This guy broke math, so this guy fixed it. Hello and welcome back to set theory. In the last part, we went over the first two axioms, that is empty set and extensionality. Today, we're going over infinitely many axioms in one video. We're going over the axiom schema of separation. And schema means it's not one axiom, but it's a recipe for an infinite number of axioms. The reason you get an infinite number of axioms is because for every possible property P of X you could come up with, you get a different axiom. And I'll explain later a little more what I mean by property. So let's decipher this. This says for any A, there exists a set B, spoiler alert, it's going to be a subset of A, such that the elements of B are precisely those members of A for which P of X is true. This part right here essentially says that B is the set of elements in A for which P of X is true. So B is this subset. Since by the axiom of extensionality, we know two sets are equal if and only if they have the same elements, this notation is not ambiguous, so we can reuse it. In other words, for any property P of X in any set A, this set exists. Let's look at some examples, shall we? This is an axiom of set theory. Here we substituted the formula X is not equal to X in place of P of X. In other words, for any set A, this set exists. Note that this set has no elements since nothing can be not equal to itself. By the way, this proves that if some set exists, then the empty set has to exist as well, which is why some books don't have an axiom of the empty set. They just have an axiom that there exists some set instead. Because if there exists some set, then the empty set must also exist by the axiom schema of separation. Let's look at another example, shall we? This is another axiom of set theory. Here, our X is non-empty is our P of X. Now, this may look like I'm cheating because I'm using English here. However, in principle, we can rewrite this with quantifiers. That's better. In other words, if you have a set A, then this set exists as well, the set of elements in A which are non-empty. Let's look at another example, shall we? By our schema recipe, this is also an axiom of set theory. Notice this example is a little bit different from the previous two, because in the previous two, X was the only free variable, where in this example, the P of X, besides using X, it also refers to another set C. And I never explained before exactly what I mean by the word property, but when I say property, I mean that our property P of X, it can refer to other sets as well, not just X. So we can have C or other sets as well. In other words, for any set C in A, this is also a set, the set of things in A which are also in C. You may notice that this is just the intersection of the sets A and B. This little symbol here means intersection. Now, you may have noticed that the C is missing a quantifier in this formula. Here, we're using the convention of universal closure, which means if you have a variable like this, which is missing a quantifier, there's really an invisible universal quantifier at the beginning. Or if you prefer, we can use English to say for all free variables other than X that occur in our formula here. Let's look at another example. This is also an axiom of set theory. Besides X, our property depends on two other variables, C and D. Just to be super clear, if we want to, we can write our property like this to show that it depends not only on X, but also on C and D as well. Either notation's fine. You may have noticed that our C and D are technically free variables in this formula. So what this really means is that for all sets C and D, this is true. So in other words, for any set C and D in A, this set exists. In general, the Axiom schema of separation can be stated more formally like this. For any formula where the free variables are not just X, but potentially also a bunch of other ones, these W's, this is an axiom. In our previous example, our C and D are like W1 and W2. And our formula depended not only on X, but also on C and D as well. Or in this case, W1 and W2. It doesn't really matter what you name them. For reference, let's compare that to my version of the axiom schema. As you can see, my version, this, is a lot less intimidating for new students than this. However, the trade-off is that with my version, you have to understand what the word property means. The more formal version makes it very clear that this P of X can depend not only on X, but other sets as well. Now, this is important. When we say property, that means P of X is allowed to refer to other sets as well, not just X. However, it's not allowed to refer to B. Notice in the more formal version, our formula can have X in it, and it can also have a bunch of other variables in it as well, but it can't have B in it. The reason the property is not allowed to refer to the set B is because it would lead to a self-referential paradox. What's the problem? Why can't it refer to B? Why can't our property of P of X have a B in it in general? And the reason is because sometimes it leads to contradictions. For example, assume this were true. If our properties were allowed to refer to B, then this would be our P of X, and this would have to be an axiom of set theory. So it's true, right? Well, here's the problem. If this statement is true for any set A, then it has to be true if A is the empty set as well. So that means this is true. Now, since X is a member of the empty set is false no matter what, and since this wedge means and, that means whether or not this circled part is true depends solely on whether or not this part is true. So we can simplify our expression. So our expression turns into this. And do you see the problem with this? Here, these are mutually exclusive. If one's true, the other's false. So the compound statement is false. Therefore, we're saying there exists a set B such that for all X, some false statement is true, which is absurd. So this is a contradiction. So moral of the story, our P of X cannot refer to this B. That kind of makes sense because this part of the axiom just means B equals the set. And it would be kind of weird if this P of X could refer to the whole set itself. Now you may be wondering, well, okay, P of X can't refer to B, but can it refer to A instead? Can it refer again to this A in this formula P of X? And the answer to that question is yes. And here's why. If we look back at the logic version, it might not be totally obvious why. But first of all, I want to let you know that there's actually different versions of the logician's version. And the version on Wikipedia actually allows A to be a free variable. So let me write this in blue. There's a version of this axiom schema that allows you to include the A among the free variables. However, even if you don't allow that concession, there's a way you can get around it. Let me show you a little example how you can do that. For example, let's say we have this statement. Can we guarantee that this set exists? Here, our P of X has an A in it, you'll notice. Well, let me show you what we can do. By the axiom schema of separation, we know that this is true. And notice this P of X doesn't have an A in it. Now, here's the thing. We know that this set exists for any C and A in our universe. And this is true even in the special cases when C and A happen to be the exact same set. So this statement is actually stronger, and therefore this weaker statement has to be true as well. So moral of the story, P of X can have an A in it, and it doesn't really cause any issues. So now moving forward, let's prove a theorem. This is sometimes called Russell's paradox. The theorem says there is no set of all sets, or in quantifier logic, there does not exist a set V such that every set X is also a member of V. This symbol right here means not, by the way. Towards a contradiction, assume that there is a set of all sets V, such that every set is a member of V. By the axiom schema of separation, this set must exist. Here is our property P of X. Let's call this set S. Now, either one of two possibilities has to be true. Either S has to be a member of itself, or S has to not be a member of itself. And spoiler alert, I'm going to show that both of these possibilities lead to a contradiction. Let's handle this one first. Assume S is a member of itself. Well, since we defined S to be the set of things in V which are not members of themselves, what does that tell us? That tells us two things. That tells us that S has to be a member of V, and S is not an element of S. So this doesn't make sense, right? Because we assume this is true, but then we prove that it wasn't true. This contradicts our assumption S is a member of S. Since we said earlier that one of these possibilities must be true, since we know this one's false, that means this has to be true. So that means S is not a member of S. However, here's the thing. We know that S has to be a member of V. Why is that? Because we assume that V is a set that contains every other set. So S has to be in V. And here's the problem. If S is in V and S is not a member of S, that means S has to be a member of this set, because this set is the set of things that are in V and are not elements of themselves. If you satisfy those two conditions, you're in the set. If you don't satisfy them, you're not in the set. So S has to be in this set. And what is the set called again? Oh, look, it's called S. And see the problem here? On the one hand, S is not a member of S, but on the other hand, S is a member of S. So this is a contradiction. So no matter what happens, we get a contradiction. So therefore, our assumption that there is a set of all sets was wrong. Therefore, there is no set of all sets. Now, here's an important thing to note. A set of this form will always exist by the axiom schema of separation. However, the set of all sets satisfying P of X doesn't always exist. Sometimes it exists and sometimes it doesn't. For example, this set doesn't exist, the set of all sets that are not members of themselves, because if it did, we would get a similar contradiction as in the proof we just did. Similarly, this doesn't exist. If this existed, it would be the set of all sets that are equal to themselves. And since anything's equal to itself, if this did exist, it would be the set of all sets, which we just proved can't exist. However, this guy actually does exist. Why? Because this is the set of all sets that are not equal to themselves. Now, it's impossible to be not equal to yourself, right? So therefore, this is the empty set. This doesn't have a single element. And so since we know the empty set exists, we know this set exists as well. Another example, there is a set of all sets which are members of both A and B simultaneously. The reason for this is that we can rewrite this set like this. It's the set of all X and A such that X is an element of B. Here, X is an element of B. This would be our property P of X. So we know that this guy exists by the axiom schema of separation. But there's actually another way we can rewrite this and get the same set. We can also rewrite the set like this, the set of all X and A such that this property is true. We know that this exists by the axiom schema of separation. Now, if you're an A and B, well, then you're automatically an A anyway. So saying A is an element of A is a little bit overkill. It's a little bit more writing than we really need, right? So therefore, since we know that this implies X has to be an A, that means it's safe to write this. That means this is a set. Let me summarize that rule for you. Whenever you have some set existing such that for all X satisfying a property, X has to be in the set, then you know that the set of all sets satisfying that property has to exist. If the property can never be true, if you're not an A, then we can rewrite this as just the set of things in A for which P of X is true. And we know this exists by our axiom schema, so therefore this has to exist as well. Now, one thing you may have been wondering if you've ever seen any other books is why there's so many names. Why do different books call this axiom schema by 4.5 different names? The name separation, which is the one that I'm using, was given to us by Zermello. The intuition is that by taking a subset, you're separating the elements that you want from just the rest of the elements of the set. The name specification kind of has a similar meaning. The idea here is that you have a set A and you're specifying which elements you want. I think whoever invented the name specification thought that it would be easier for students than separation. Ironically, the end result seems to have been making things harder for students because now students have all these different names floating around and they get confused. The least intuitive name is probably comprehension. In Latin, it means something like to seize. So I guess the idea is you have a set A and you're seizing the elements you want. It's sometimes called restricted comprehension to contrast it with unrestricted comprehension, which refers to how in the old days they thought that anything that looks like this is a set. This one's called unrestricted because X can be any set, whereas this one's restricted because it has to be already a member of some set. Finally, this is especially informally called the axiom schema of subsets because that's what it does. Given a set A, you can form a subset of A consisting of all the members of A satisfying a certain property. So here are the axioms we've covered so far. Using these three axioms, or, well, technically this is infinitely many axioms, depending on how you want to think of it, we were able to prove a few basic facts of set theory. But here's a question. Does anything other than the empty set exist? If you think about it, from these three axioms alone, we can't answer the question. We know that there exists an empty set. By axiom extensionality, we have a criterion for comparing whether or not two sets are equal, so we know that there must only be one empty set. And then separation helps us to form subsets, that is, quote unquote, smaller sets of sets that we already have. But so far, we can't even prove that other sets, such as the set containing the empty set, exist. To do that, we're going to need some more axioms which allow us to build bigger sets from smaller sets. So that's where we're headed in the next lecture. Stay tuned for the axiom of pairing.